Hey guys, welcome back to a new video. This session will be the first one in a 5-part series on complex numbers. We will start out very basic by looking at doing algebra with complex numbers. And more specifically, in this session, we'll be solving exercises on adding, subtracting, dividing, and multiplying complex numbers. The timestamp for each topic and exercise can be found in the comment section below, where you can also ask any question you have along the way. Before we get into the exercises, let me first briefly define what a complex number is. A complex number consists of the sum of two parts. We have a and b being real numbers, so any number you like, and this I is the imaginary number, which has the special property that I squared is equal to -1. We call this first part the real part of our complex number, and the second one we call the imaginary part of our complex number. And with that intro out of the way, let's get into the first exercise. In the first part, we are going to look at addition and subtraction of complex numbers. The first exercise is where we have to add 3 plus 5i, which is a complex number, plus 1/2 minus I. And here we already come across the first principle and the most important principle about complex numbers, which is that in the case where we have to add or subtract or do any operations between two or more complex numbers, we always compare the real parts with each other and the imaginary parts with each other. And we separate these parts when doing the operation. In this case, we, for example, first add the real parts, so we get 3 plus 1/2, and then we simply add the sum of the imaginary parts, which becomes 5i minus I. And at this point, we can simply do the calculations. So we have 3 plus 1/2, which becomes 7/2. And then we do the same for our imaginary part. We have 5 times I minus 1 times I, which simply becomes 4 times I. And here we already have the sum of our two complex numbers, which is again in its own a complex number. This will be the real part, and this is of course the imaginary part. Let's look at a second exercise, where we have a first complex number, which is 1 plus 3i, and we subtract from this 5. Now we see that we have the real parts being 1 and 5, and the imaginary part being 3i, and here simply 0, because 5 can be seen as a special type of complex number without an imaginary part. Using again the same principle, that we do the operation on the real parts and the imaginary parts separately. Then we get for the real parts 1 minus 5, and for the imaginary part we have simply 3 times I. And this of course becomes 1 minus 5 is -4 plus 3i. Again a complex number with the real part being -4 and the imaginary part being -3. Let's do a third and final exercise on addition and subtraction, where as the first complex number we have -3 plus 5i. And we subtract from this 2i plus 5. Again, these are two complex numbers, which each a real part, and we see that in this second complex number, the real part and the imaginary part are actually placed in a different order, but that doesn't really matter. And we have, of course, a imaginary part. Again, doing the operation, in this case, a subtraction, with the real parts, we get -3 minus 5. And doing the same with the imaginary part, we get 5i minus 2i, which simply gives us -8 for the real part and plus 3i for the imaginary part. So these were exercises on addition and subtraction of complex numbers. They are very straightforward, but still incredibly crucial. Let's now look at how to multiply and divide two complex numbers, which is a bit more involved, but if you still apply the same principle, then it will be all right. For the first exercise, we have to multiply 3 minus 1/2 I together with the complex number 1 plus 5i. And so how are we going to tackle this problem? Well, we're going to use the distributive property of complex numbers, which basically says the following. So the resulting of this multiplication between these complex numbers will be, first we multiply 3 and 1, so we get 3 times 1. Then we multiply this 3 with this 5i, so we add to this 3 multiplied by 5i. Then we multiply this minus 1/2 times I with this 1. So we get minus 1/2 I times 1. And finally, we multiply this minus 1/2 I with 5i. So we subtract from this minus 1/2 I multiplied by 5i. And this is of course the basic distributive property that you would use if you would multiply two brackets with each other. So we can calculate this. We get 3 for the first term plus 15i for the second term minus 1/2 I for the third term. And for the fourth term, we have to be careful. So we have minus 1/2 times I multiplied by 5 times I. So how are we going to do this? Well, we're first going to multiply this 1/2 with this 5. So we have 1/2 multiplied by 5. And then we multiply this I with this I. So we get I squared. However, we know of course that I squared is equal to minus 1. So we need to take this into account. So we get 3 plus 15i minus 1/2 times I is of course 29 divided by 2 times I. And now we have this last term where we have 5 divided by 2 times I squared. But I squared is minus 1. So we get minus 5 divided by 2 times minus 1. And of course, because this minus 1 and this minus sign here can cancel each other out, we simply have the following. We have 3 plus 5 over 2, which is this 5 over 2 right here, plus 29 divided by 2i, which can of course be rewritten as 11 over 2 for the real part, plus 29 over 2i. And we see here that the multiplication of two complex numbers is again a complex number, with the real part being 11 over 2 and the imaginary part being 29 over 2 times I. Let's now go to the second exercise where we have to multiply I together with minus 2 times I minus 5. So again, the multiplication of two complex numbers. However, one complex number only has an imaginary part, and the other complex number has both a real part and an imaginary part. But that shouldn't throw us off guard. So we can simply multiply this by first multiplying this I with this 2i right here. So we get I multiplied by minus 2i. And then we multiply this I with this minus 5. So we get minus 5i. Again, rewriting this, we get minus 2 times I squared, because we multiplied this I with this I. And we subtract from this 5i. Now again, we know that I squared is minus 1, meaning that we get minus 2 multiplied by minus 1, this I squared, minus 5i. And this is of course 2 minus 5i. Again, a complex number with a real part and an imaginary part. Let's now go to the next exercise, where we will calculate a property of complex numbers that we will actually use quite a lot. So we multiply the complex numbers 5 plus 4i together with 5 minus 4i. And what is special about this multiplication is that we see that the real part of our two complex numbers is equal. However, the imaginary part is opposite in sign. We have plus 4i and minus 4i. So let's see what this multiplication becomes. Again, we use the same procedure by first multiplying these two 5's together. So we have 5 times 5. Then we multiply this 5 with this minus 4i. So we have minus 5 multiplied by 4i. We then multiply this 4i with that 5. So we have plus 4i times 5. And to end off, we multiply this 4i with this minus 4i. So we have minus 4i times 4i. So what does this now become? We have 5 times 5 is simply 25. We have minus 5 times 4i, which is simply minus 20 times I. We have 4i times 5, which is plus 20 times I. And then of course we have minus 4i times 4i, which is 16 when we multiply these two 4's together, and of course I squared. But of course, I squared is equal to minus 1. So this I squared can be replaced with minus 1, and the minus 1 makes from this minus sign a plus sign. So we see that we get 25 this minus 20i cancels with this plus 20i, and the only thing that is left is this plus 16. So we get 25 plus 16. And this is actually a purely real number. We only have real parts. We have 25 and 16. And we can actually write this a little bit different. Let's write this as 5 squared plus 4 squared. And from this we can see that if we multiply two complex numbers where only the imaginary part has an opposite sign, here plus 4i minus 4i, that the result will be the square of the real part plus the square of the coefficient in the imaginary part. And the result will be a purely real number. As a last exercise on multiplication, let's look at how we square a complex number. So let's say that we have the complex number 2 minus 3i, and we have to square this one. We know that squaring a number is simply multiplying this number with itself. So we have 2 minus 3i multiplied with 2 minus 3i. And at this point we know the drill, we just use the distributive property. We multiply this 2 with this 2, which simply becomes 4. Then we multiply this 2 with this minus 3i, which becomes minus 6i. Then we multiply this minus 3i with this 2, which also becomes minus 6i. And then we multiply, of course, this 3i with this 3i, which becomes plus 9 times I squared. But we know that I squared is equal to minus 1. So this I squared becomes a minus 1, and this minus 1 makes from this plus sign a minus sign. This gives us 4 minus 9 minus 12i, or written differently, minus 5 minus 12i. So if we square this particular complex number, we again get a complex number with a real part being minus 5 and an imaginary part being minus 12i. Having now taken the square of this complex number, what would be the square root of the same complex number? Well, turns out that this is a bit more involved, and this is exactly what we will do in the next video. However, before we can tackle such issues, let's first look at how to divide two complex numbers. In the first exercise, we have to divide the complex number 2 plus 3i with 5 plus 4i. And if we now want to divide these two complex numbers, we first need to ask ourselves, what do we actually want to get from this division? Well, what we ideally want to get is another complex number, meaning something of the form a plus b times I, with a real part and a complex part. So how can we rewrite this fraction as something like this, thereby becoming a very easily identifiable complex number? So we could easily split the enumerator, and therefore we get 2 divided by 5 plus 4i plus 3i divided by 5 plus 4i. However, this is not in this form. We cannot identify a real part without an I and an imaginary part with an I. And we see that the thing that really bothers us is this 4i in the denominator. So what we actually want to get is a real number in the denominator. So how do we do this? Well, we first rewrite what we already have. So 2 plus 3i divided by 5 plus 4i. And what we now do is we multiply this with 1. Well, not really with 1, but with a fraction that will be 1. So with 5 minus 4i divided by 5 minus 4i. And again, of course, this is simply 1. A number divided by itself is, of course, 1. If we do this multiplication, we first look at the denominator. Again, we use the same distributive property to multiply all of these numbers together. So in the denominator, we first get 5 times 5 is 25. We multiply 5 with minus 4i, which becomes minus 20i. Then we multiply 4i with 5, which becomes plus 20i. And eventually we multiply 4i with minus 4i, which becomes minus 16i squared. And of course, this looks a lot like what we had in a previous exercise, where we multiply a complex number with another complex number where only the imaginary part changes sign. So we actually already know what this will become. So we get for the first term 10 minus 8i plus 15i minus 12i squared, where I just used the same procedure. Rewriting this, we get the following. Again, in the denominator, we simply get 25 plus 16. And why? Well, because these two terms cancel each other out. This I squared becomes a minus 1, which makes this minus sign a plus 1, and this 25 simply remains the same. And we see here that we exactly have the property that we expected when we multiply these specific two complex numbers together. We see that we get a simple real number, which is exactly what we wanted in our denominator. And that's also the reason why we chose to multiply our fraction exactly with this fraction, simply to get in the denominator a real number. In the enumerator, we simply get 22, which is this 10 plus minus 12 times I squared. This I squared becomes a minus 1, so minus 12 becomes plus 12. And we add to this 7i, which is simply minus 8i plus 15i. And we see that we now exactly have what we wanted. In the enumerator, we have a complex number, 22 plus 7i, and in the denominator, we have a purely real number, in this case 41. And therefore, we can split this fraction in two parts. We have 22 divided by 41 plus 7i divided by 41. And therefore, we now have a complex number with a real part and an imaginary part, which can be very easily identified. So what we actually did was rewrite this fraction without a clear real and imaginary part as this sum of two fractions, the sum of a real part and an imaginary part, which in total is a complex number. And because this technique might sound quite confusing, let's practice it another time in the second exercise. Here we have to divide 1 minus 3i by the complex number 2 plus 3i. And again, the first step here is to note that we want a real number in the denominator, because then we can split this fraction in a real part and an imaginary part. To get a real number in the denominator, we multiply the denominator with the same complex number, however now the imaginary part has a switched sign, so 2 minus 3i. And of course in the enumerator we also have to put the same number in order for this fraction to be 1. And now it simply boils down to multiplying both these two terms in enumerator and denominator. In the denominator we get the following. 2 times 2 is equal to 4. 2 times minus 3i is equal to minus 6i. 3i multiplied with 2 is plus 6i, and 3i multiplied with minus 3i is of course minus 9 times I squared. However, we could have easily used the property that we already know, which is that the result of such a multiplication between these specific two numbers is simply the real part squared, so 2 squared is 4, and we add to that the coefficient in the imaginary part squared. So we add to this 9. And this actually saves us quite some calculation work. In the enumerator, we have of course 1 multiplied with 2, which is simply 2. 1 multiplied with minus 3i, which is of course minus 3i. Minus 3i multiplied with 2 is minus 6i. And minus 3i multiplied with minus 3i is of course plus 9i squared. So what we get is 2 minus 9, because plus 9 times I squared becomes minus 9, minus 9i. And we divide this of course by 13. And rewriting this even further, we get minus 7 divided by 13 minus 9i divided by 13. And we see here that we indeed split our fraction in a real part and a imaginary part, and thereby receiving a complex number. An interesting application of this procedure is to calculate what exactly is 1 over I. Well, we simply do the same procedure, so we get 1 over I, and we multiply this with 1. However, this 1 being written as a fraction. We simply multiply this denominator with the same complex number, however now the imaginary part has to swap signs. Since the imaginary part is the only part that we have, this I has to swap signs to minus I. And in the enumerator we of course have the same minus I. This simply becomes minus I in the numerator divided by minus I squared. However, we know that I squared is simply minus 1. So we have minus minus 1. And minus minus 1 is simply equal to plus 1. And now if we divide by plus 1 is simply doing nothing. So we have minus 1. And from this, we see that 1 over I is simply equal to minus I, which is a relation that is oftentimes forgotten or very confusing. But now you know how it is obtained, which makes it much easier to remember. And this brings us to the end of this video, which was an introduction on complex numbers. In the next video, we'll be looking at taking the roots of complex numbers and solving second-order equation with complex numbers. If you enjoyed this video, give it a thumbs up, and if you want to get notified by future releases, consider subscribing. And with that, I thank you for watching, and I will see you in the next one. Bye.